Welcome, mathematicians. For those of you who are new to the channel, I made a clickbait title. I'm not quite a PhD yet. Not for another, my defense is in 8 days. So technically, okay. Not really. It's a PhD student doing a midterm. But I'm an instructor for Discrete mathematics course, and I gave my students a midterm this past week. So I figured I may as well make a video out of the solutions. And there's some moderate authenticity to the solving of this because I didn't actually create the midterm. Of course, I looked over it while the students were doing it. But the other instructor for the course, picked the question. So without further ado, let's dive in. Let's see what the midterm looks like for my discrete math course and how to solve it. So the first one that we're doing is the Euclidean algorithm. We're using the Euclidean algorithm to determine the GCD of 123 and 70. And then we would also like to produce integers a and b such that 123 times a plus 70 times b is equal to the GCD. Okay, so we get 123 equals, so we're just doing the Euclidean algorithm. How many times does 70 go into that? Once. What's the remainder? 53. So we move over 70, and we move over 53, and we ask ourselves the same question. Clearly 53 goes in there once. What's the remainder? 17. So we move over 53, and we move over the 17. And how many times does 17 go into 53? 3 times. 3 times 17 is 51. So we have 2 left over. So we move over the 2 and we move over the 17. How many times does 2 go into 17? Goes in 8 times because 2 times 8 is 16. So we have 1 left over. And then we move over the 2 and we move over the 1. And of course, this is just 1 times 2. This is 0. So we know our GCD is equal to this. And we're going to go 1 layer down to apply the table method so we can come up with our A and B. So without doing any thinking, we put a 1, 0. We put a 0, 1. Then we ask ourselves, how do I combine these 2 rows to get the next row? Well, the entry here in row 3, it's row 1 minus row 2. So I do that operation. I do row 1 minus the entries in row 2. So 1 minus 0 is 1. 0 minus 1 is minus 1. Then I go over, I look at 17. How did I produce 17 from 70 and 30? Well, again, I just subtract 53, so the entry in row 3 from the entry in row 2. So I'm going to do those same operations here. So it goes 0, subtract 1 is minus 1. 1 subtract minus 1 is 2. Yeah. Okay, then I go to the next row. Now it's 8, right? How do I produce 2 from the 2 rows above? Wait, no, not quite yet. No, this is 3. This is the subtract 3, right? I subtract off 3 times 17, so I'm going to subtract off 3 times this row from this row. So 3 times negative 1 is negative 3. I'm subtracting that off, so I'm adding 3, so it should be positive 4. And then 2 times 3 is 6. But I'm subtracting that off, so I should get minus 7. And then I got to do one more step. How did I get the 8? How did I get 1 out of here? I had to subtract off 8 of these 2's. So I have 4 times 8, which is 32, but I'm subtracting that off, so I'm going to have negative 33. And minus 7 times 8 1 is 7 times 8, 28, 56. So that's 56. I'm adding 56 though, so it should be positive 58. And okay, so that should be our answer. So we would say something like, thus GCD 1, 2, 3, 70 is equal to 1, and A equals minus 33, B equals 58 is a solution to 123 times A plus 70 times B equals 1. In fact, this is a midterm. We want to check our work. We want to make sure that we're getting things correct. So let's even do the computation. Indeed, 123 times minus 33 plus 58 times 70 times, it doesn't matter, it's the same thing, but I like to be consistent with where I put my parentheses, times 58 is equal to so 30 times 123 is going to be minus 3690 minus 369 plus 7 times 5 is 35, so that's 3, but call it now 70 times 50, you got to tack on a couple zeros there. 7 times 8, we just did that, that's 56, so that's 56, but we tack on a 0 because it's 70 times 8. Great, so now I'm going to combine these two to make the numbers less scary. So that's minus 190. And then I'll combine these two to make the numbers less scary. So 560 minus 360 is 200. Minus 9 is 191. And indeed, that works out to 1. Awesome. Okay, so we're done question 1. Question 2 is proved by induction, proved by contradiction that for all integers n, if n squared plus n is odd, then what? N is odd. Okay, so there's two different ways we could approach proof by contradiction here. So let me show you method number 1. So this is the way I would prefer to do it, but there's a second way that we could do this. So because by a proof by contradiction means we can use it in different ways. So essentially it is either you can set up the statement and reach the conclusion by contradiction, or you could suppose the entire statement was false in order to obtain a contradiction. You'll see what I mean in a second. So I could begin this proof normally, without even thinking. I see that universal quantifier, so I say let n be in Z, and because I want some hypothesis on n squared plus n, I'll put comma such that n squared plus n is odd. Now I'm going to do a proof by contradiction because I've set up the problem. I'm trying to prove the conclusion. So I would like to do that with a proof by contradiction. So I say assume, for the sake of contradiction, that n is even. So I've told my students we're allowed, of course, to assume that not odd is equivalent to even. We've proven that in class. So assume for the sake of contradiction that n is even. Okay, so what do we do now? We have to unpack some definitions here. Well, what does it mean for n to be even? So by definition, we can choose k in the integers such that n is equal to 2 times k. Okay, so we have some information about n. We know that we're fishing for a contradiction here, and we need to turn this into some information about n squared plus n. I mean, well, we don't necessarily need to, but we know something about n squared plus n. We're assuming that something's going to go wrong if n were even. And somehow we need to connect these ideas. We need to make some things be at odds with each other. So let's try and see what would that apply. So thus, n squared plus n, well, if we substitute it in, the fact that this is even, right? Then we get, this is 4k squared plus 4k, which is, let's say, 2 times, because I want to exactly pattern match the definition of being even, 2 times this. So now we see the problem, right? And this means that n squared plus n is even. Why? Well, again, I want to exactly pattern match the definition of even. So I say since, but notice I don't have to repeat the definition of being even verbatim. Since this is an integer, n squared plus n is even, which contradicts. So whenever we're doing a proof by contradiction, we want to be very precise about what is the thing we're assuming for the sake of contradiction, and what specifically is the contradiction that is obtained. So, which contradicts the assumption, that n squared plus n is odd. Right? So, therefore, our assumption that n can be even must have been faulty. And thus, n is odd. Okay, so that's approach number 1 to this problem. The other way that you could do it, is deny the entire thing. So the other thing you could do is say, so option number 2 to solve this problem is you could say, suppose, for the sake of contradiction, that, and now we assume the negation of the entire statement, right? So we assume that there exists an n in the integers where n squared plus n is odd, but n is even, right? That's just taking the negation of the statement that we want to prove, right? And now the proof actually from here follows almost entirely. Now you could launch into unpacking what it means for n to be even. I personally just think that philosophically it's a little bit nicer, because right now this is just saying that there exists an n, and we technically haven't fixed the n. So I would just say something like, fixing an n. Maybe we would even use a different notation. We could call it m, just to say, so fixing an m or choosing an n such that n squared is odd and n is even by definition. And now we just do the exact same proof as above. By definition, we can say something about n, yada, yada, yada. And so the only difference now is in our proof when we get to the very end, right? When we say therefore our assumption that, so so therefore our assumption that there exists, so therefore our it's the entire statement itself that was incorrect. So therefore the assumption that there exists where n squared is odd, but n is even, must have been faulty, or we could even say, I would say, we could even say must be false, hence the negation is true. So hence, for all integers in here, n squared plus n is odd, implies n is odd. Okay, so that's two barely different ways of solving that problem. So next, we're going to go on to what's this problem here? So for all sets ABC, for all sets ABC, so we have to prove or disprove the statement. So we have to first figure out if it's true or not, and then we have to try to prove it. So for all sets A, B, C, if A is a subset of B union C, then either A is a subset of B or A is a subset of C. So we need to figure out if this is true. So I don't want to write my good copy, right? My good copy. So over here, everything to the left of this white line, that's going to be my good copy. My rough work, and the stuff I'm not handing in, I'm putting on the back of the page or something. My rough work is going to be over to the side here. No, what do I want? I thought I had a purple or something. Let's go dark teal, fine. Slightly more evil version of blue. So how do we do this, though? So a picture is not a proof, but of course a Venn diagram can help us to prove this. So we're going to write A, B, C. And now we're going to ask ourselves, well, so how do I set this up? If A is a subset of B union C, right? So B union C is sort of gluing together these two rings. What would make that true? Well, certainly I should not be allowed to have any elements in here, right? So this thing should be empty, right? That would force A to be a subset of B, of the union of B and C, if there's nothing in that region. Okay, so now is it true? Is it true if there's nothing in this region, does it have to be the case that either A is a subset of B or that A is a subset of C? Well, it seems that perhaps not, because if I took something here, right? If I took something here, that would be an element that is in, that would sort of prevent A from being a subset of C. But you could say, well, that doesn't prevent A from being a subset of B. However, if I took something else here, then that would, right? So how could I possibly construct such an example? So I'd want, again, we're thinking like mathematicians, we want to construct a minimal such example. So what could I do here? Well, perhaps if I took A to be the set containing 1 and 2, so this would be 1 and this would be 2. So what do I have to take for B? So B should definitely contain 1. C should definitely contain 2. Can I get away with, is this enough? Is this the smallest example I could come up with? Well, if B and C were just the sets 1 and 2, their union is A. So then A is a subset of B union C. But clearly A is not a subset of B or C because it has less elements, right? So this is good. This is good. Okay, so we can use this in our proof. So now let's go back over to our good copy. In this class, I'm asking the students, when we disprove a statement, we want to first write out the negation and prove the negation. So we would say something like, this statement is false. The statement, or even I prefer to say something like the above statement, because this is kind of, sometimes you get into problems being too vague if you say that in mathematical writing. So the statement is false. The negation, we will prove, let's say, we will prove the negation, which is what? The statement that there exists sets A, B, and C, where A is a subset of B union C, but A, so we have to think about where we have to negate the other part, right? So the negation, when it distributes over an or, it becomes an and, but A is not a subset of B, and A is not a subset of C, right? So that's a statement that we want to prove, right? So an existential statement begins with us having to give examples, but we already cooked up some examples over here, right? So we can make some definitions, right? We can make some definitions. So define A to be the set 1, 2, B to be the set containing 1, and C to be the set just containing 2. Okay, so we've taken care of the existential part, right? We've constructed some sets that we claim are going to do the job. Now we must verify that A is a subset of B union C, but we could go something like, hence, A is equal to the set containing 1, 2, which is equal to the union of the set 1 and the set 2, which is the union of B and C. Hence, A is a subset of B union C. Fantastic. But now we need to show that A is not a subset of B and A is not a subset of C. Now again, you don't need to repeat the full definition of not a subset, but in order for us to deliver a correct proof, we should remind ourselves on a scrap paper, what does it mean to say that A is not a subset of B? Well, what this really means is it's the negation of the statement that A is a subset of B. And what is the statement that A is a subset of B? That's really a shorthand for saying for all A in A is in B, right? So in other words, the negation of that becomes that there exists an element of A where A is not an element of B. So, to be precise, we should say something like, moreover, so we should, to really prove this, we should actually specify those elements. Moreover, 2 is in A, but 2 is not in B, so A is not a subset of B, and 1 is in A, but 1 is not in C, so A is not a subset of C. And there we go. That's the proof. That's the proof. Okay. So the next question. Now sometimes, okay, if it's a midterm, I wouldn't worry about the denouement, right? The final line that you add that says, hence we've proved blah, blah, blah. But let's, we're doing a midterm. We're in a time crunch now. Let's skip it. The next statement is, the next statement is for all sets A, B, and C, if A set minus B is a subset of C, then A set minus C is a subset of B. I think we might have even done this one in class, but definitely I know from the few students that show up to my office hours, I know that this one is in the homework problems. And so if you did the homework problems, you would already know that this statement is true, and you would already know the exact proof strategy of how we're going to do it. But let's put ourselves in the shoes of someone who maybe didn't do the homework. And let's say, okay, how do I figure out that this is true? Well, I'm going to draw my little Venn diagram again. A, B, C. How could I cook this up? So I need A minus B to be entirely contained in C. So if I look at A and I take away all of the stuff that's in B, well, I can't have anything out here again, right? If there was anything in this region I'm shading in red, then A minus B would not be a subset of C, right? So definitely A has to look like this by my hypothesis, right? As long as I take A minus B, as I take that out, now it looks like A minus B is a subset of C. Great. Now, is it necessarily the case? If I look at what remains of A and I took away C, is what remains going to be a subset of B? Well, yes, because this blue part right here is exactly A take away C in this situation. So yes, A take away C is a subset of B. Okay, so this statement is true. So let's say the above statement is true. The above statement is true. Proof. Again, don't even have to turn on my brain yet. For all sets, so I say let A, B, C be sets. And I don't want just any sets, of course. I want sets that satisfy the hypothesis. So I say let A, B, C be sets where A minus B is a subset of C. Okay. And what am I trying to prove? So again, I'm going to go over to my notes, to my rough work here to remind myself, well, A minus C being a subset of B, what does that really mean? That really means for all A in A minus C, A is an element of B. So how do I prove that? I'm going to have to begin with a let statement, right? So I begin by grabbing an element. So let's let A be an element of A minus C. Now, how do we proceed with the rest of the proof? You could go ahead and try and prove it directly. What you will inevitably find is you will get stuck. And as I've said many times in this course before, when you get stuck, what's one of the things that you do when you're stuck is you think about, how do I change my proof strategy? That is, how do I think about the statement, changing the statement that I'm writing? Could I do a contrapositive, or could I do a proof by contradiction, right? Could I do a contrapositive, or could I do a proof by contradiction? And so now we will lapse back into the state of a student that did do their homework and knows that a proof by contradiction is coming here, right? So we've assumed that we have our element of AC, and our goal is to prove that that element must be in B. And so we'll suppose, for the sake of obtaining a contradiction, that it was not in B. Okay, so assume, for the sake of contradiction, it's very important to tell our reader what we're up to. Assume, for the sake of contradiction, that A is not an element of B, right? Assume for the sake of contradiction that A is not an element of B. Okay. What can we do with that information? Well, looking at this, we have A minus B is a subset of C. That's one of the assumptions that we're working with, right? So again, I don't want to sully my good copy with a bunch of like nonsense, but I know that A minus B is a subset of C. What does that mean? What does that mean? That means that if I had some element that was in A and was not in B, then that would force that element to be in C. Okay. So I have one element that I'm hanging on to here, right? That's my, this A, right? Let A be in A minus C. Assume for the sake of contradiction, A is not in B. Oh, A is not in B. That has something to do with this. And by the way, if A is in A minus C, then little a is in A. So actually, I could say something like, since... Now, this is also a part in the proof where you might have recognized, oh, maybe I should have unpacked this definition immediately. No worries, you could go back, erase it, or we could simply just remind the reader, since A is in A minus C, A is in A, and A is not in C. So then we could say something like, as A is in A, and I know we just said it a sentence ago, but to be really nice to the reader, let's remind them, to really match it up with the definition of A minus B. As A is in A and A is not in B, A is in A minus B. And we know, and by assumption, we could even say, because that is one of the assumptions in our problem, we could say by assumption, A minus B is a subset of C, hence A is in C. Okay, so we just did some stuff, but who cares? Why did we do that? I mean, we saw something that we could get the hypothesis involved. We've changed the state of knowledge that we have. But so let's look back over and review things. Wait a second. I just realized somewhere along the way, I noticed that we were able to argue that A is not in C, but we just reached a conclusion that says A is in C. That's a contradiction, and that's exactly what we were looking for. So hence A is in C. So I might say comma, which contradicts. Now notice in the previous proof, I said it contradicted one of our assumptions, right? So if I go back up in the actual proof, where was it? There was somewhere, it was in, yes, the even and odd stuff. I said that it contradicted, therefore, our assumption that here it is, which contradicts the assumption, right? So the assumption that n is odd. In this case, we're not contradicting an assumption, actually. We're contradicting a fact that we derived, right? So we're contradicting the fact that A is not in C. Now, okay, technically it's assumption because we assumed that A is in A minus C, but technically this is a fact we derived from. So, which contradicts the fact that A is not in C. Hence, so where did we go wrong? That was in, we assumed for the sake of obtaining contradiction that A is in B. Hence, the assumption that A is not in B is false. Thus, A is in B. Now here, because there's a lot going on and it's maybe been a hot minute since the reader realized what it is that we're trying to do, right? We're assuming that we have an element of A minus C and we're trying to argue that it's in B. So here I would maybe, we could remind the reader, we could say, by the arbitrary choice of A in A minus C, A is a subset of B, right? And that would be the end of our proof. Okay, we are flying through this midterm at lightning speed. Obviously, I'm going, much slower. Wow, the midterm was an hour and a half, so we still got a whole hour left to solve these problems. Obviously, I'm going much slower because I'm explaining everything out loud as I go. Okay, so question 4, next part of the exam, question 4. So we have the statement. So P is the statement. P is the statement for all integers. For all integers A, B, and C. If A divides B and A divides C, then A divides B plus C and A divides B minus C. So that is the claim. So part A asks, is this statement true? And it wants us to prove our answer. Okay, so again, this is one, well, if you hadn't done a ton of practice problems on the homework, you'd have to sit here and think for a little bit. Or if you just stop and think, okay, what does this actually mean? What is this problem trying to tell us? Well, of course, if you have two numbers that are divisible by A, you add them together, you still have something divisible by A, right? So let's go ahead and try and prove it. It is true. So maybe we should add a statement, because it's asking us, is it true? And then prove our answer. So yes, P is true. Yes, P is true. Okay. So what do we do? So we say, okay, proof. Let, again, it's a for all statement, so let ABC, I'm going to be lazy, let ABC be integers such that, because again, it's not just random integers, I want to pick integers that satisfy the hypothesis of the statement, such that A divides B and A divides C. So in these problems, you might be a little suspicious that maybe I have to worry about something to do with one of these numbers being 0 or not, because we can't divide by, doesn't make sense to talk about divisibility by 0. However, it's since we're assuming that A divides B and A divides C, it's implicit, it's baked into the definition that A is not equal to 0. But we'll see that we won't actually have to get into those technical details here. Okay. So what does that mean? I mean, we've set up our hypothesis, right? We've chosen our elements. We've set up our hypothesis. What else is there to do other than unpack the definitions? We have a very small list of assumptions here. There can't be that many options for what we have to do. So let's simply unpack these definitions, right? By definition, let's unpack the definition of A divides B and A divides C. We can choose K and L, we can choose integers K and L such that B is equal to A times K and C is equal to A times L. Okay. And what am I trying to prove? Well, I'm trying to prove something about B plus C, and I'm trying to prove something about B minus C. So I have two equations here. One involving B, one involving C. What could I possibly do to those equations to manipulate them in order to get something involving B plus C? Well, I could add those equations together, right? So hence, B plus C is equal to AK plus AL. But what am I trying to prove? So again, over on the right side of this line, right, I'm trying to prove that A divides B plus C. What does that mean? That means that there exists an m in the integers such that b plus c is equal to a times m. Okay, I have an equation with b plus c. Can I write this as a times something? Well, yeah, I've got a common factor of a, right? So now I just tell the reader, I don't need to remind them of the full definition of divisibility. I just tell the reader, well, since k plus L, and you know what? We have to do the same thing for B and C. So why don't we, well, okay, it doesn't matter. It doesn't matter, the order. So since k plus L is an integer, A divides B plus C by definition. Right? So we've proven one of the things. We have one other thing to prove. So moreover, let's tell the reader about B minus C. Well, B minus C is AK minus AL. Same thing is true. This is just A times K minus L. And so we could say, and since K minus L is an integer, A divides B minus C by definition. Right? Done. Okay, fantastic. So, we're done, right? That's everything that we wanted to prove. Okay, great. Great. We finished part A of this question. What is next for us? Well, next we're supposed to write out the converse of this statement, and we're asked if the converse is true and to prove our assertion. So for all integers, so the converse would be, so in this case, we have a for all mixed in with an implication. The for all part stays. It's just the implication that gets flipped, right? So the converse is, so let's say it this way. The converse of P, so we could say, oh, the converse of the statement or the converse of the above, that's too vague. Here we've got a name for the statement. So let's say the converse of P is, put quotation marks here, for all integers, A, B, and C. What is it? Well, it's if, now the thing that was the conclusion before, if A divides B plus C or A divides B minus C, then A divides B and A divides C. Okay. Now we've got to do perhaps a little bit more work to see if we can go backwards here. So is this statement true or not? Is this statement true or not? Well, how could we test this out? If A divides, can we cook up examples? So let's think about some like pairs of numbers. We maybe want to avoid taking zeros in this case because we're sort of worried about divisibility. I mean, definitely if B and C were both 0, then it seems that this statement holds, right? Everything's going to divide 0. B plus C will be 0. There's not much to say here. What if we took like B equals C equals 1? So let's take them both to be 1. So let's see. So if A divides B plus C or A divides B minus C, then blah, blah, blah. Okay, so let's see. B plus C would be 2. B minus C would be 0. So maybe we don't want to take that, right? Because again, well, actually maybe this would work. So let's ask ourselves, A divides B plus C. what are the numbers that we could take for that? We could take a equals 1, or we could take a equals 2. And let's ask ourselves, is it true that a divides in b and a divides c in both these cases? Well, certainly if a is 1, yeah, 1 divides everything. So yeah, it seems to work. If a is 2, oh, now we've got a problem, right? That would be the statement 2 divides 1 and the statement 2 divides 1. So neither of those statements are true. So it seems that we found a counterexample. Okay, so it's false. So let's tell the reader. So the converse of P is false. Converse of P is false. The negation, how about let's say it this way? We will prove the negation of P, the negation of the converse of P. Which is the statement that there exists integers a, b, and c where a divides b plus c, or a divides b minus c, but a does not divide b, or a does not divide c, right? So we have to remember we're negating the conclusion here, which is an and statement. So we're just trying to prove an or. So we really only need to argue that one of those two things holds, right? So we already saw from up above that the following choices will work. So choose A to be 2 and B to be equal to C to be equal to 1, right? So we've taken care of the existential part of this statement. Now we need to verify that either one of these two statements is true. Well, we need to go by definition, right? So B plus C is equal to 1 plus 1 is equal to 2 is equal to 2 times 1. So since 1 is an integer, 2 divides 2 by definition. Hence, 2 divides b plus c. Great. Okay. So 2 divides b plus c. Fantastic. So we've actually verified the hypothesis, right? Because it's an or statement. So you just need at least one of these things to be true. So hypothesis is verified. Now we simply need to argue that A does not divide B, right? We simply need to argue that A does not divide B. So remember the way that we do this formally. Okay, maybe we let you get away with something on the midterm, saying something like, obviously 2 doesn't divide 1. Here's a no-no. Here's some no-nos, I would say, some things you should not do. So probably, I haven't even looked at your midterms yet, but I'm guessing some students did this. 2 divided by 1 plus 1 equals 2 divided by 2. This is nonsense. This is bad and wrong. It doesn't make any sense. 2 divides 1 plus 1 is a shorthand for a statement. It's not equal to this statement. What else is a bad thing to do? Saying, 1 over 2 is not an integer. This is false. This is, well, sorry. It's not false. It's true. It's true, but that has nothing to do with the vertical symbol of division. This is a logical statement, right? This is a logical statement. So in order to prove that 2 doesn't divide 1, the main tool that we use is to quote the division theorem, right? So remember, the division theorem is about having something like, what do we need? We need a d bigger than 0, and it tells us that then, so for integers n and d bigger than 0, it tells us that we can always find a q such that n is qd plus r is between d minus 1 and 0, and that this is a unique pair, right? So, and then in fact, we also proved in class that the remainder is equal to 0 if and only if d divides n. So all we need to do is this number that we're claiming, which is 1 in this case, which is not divisible by 2, is simply to exhibit this as q times 2 plus a remainder of something which is not equal to 0, right? So we could say something like, however, what's our divisor here? So however, 1 is our n. 1 is equal to 0 times 2 plus a remainder of 1, where to make it clear that this is a remainder, 1 is between 0 and 2 minus 1. Hence, the remainder of 1 upon division by 2 is non-zero, and thus 2 does not divide 1. And we're done, right? Because we've now verified at least one of 2 statements in an OR statement. So we are finished with that proof. Okay, write out the contrapositive of P. Is the contrapositive of P true? So, in this case, the contrapositive of P, again, that's not going to affect the for all part of the statement. So for all integers a, b, c, now what we need to do is, so our original statement was if a divides b and a divides c, then a divides b plus c and a divides b minus c. So remember, the contrapositive of P implies Q is not Q implies not P. So we have to take the negation of the conclusion. So if A does not divide B plus C, or, so remember we have to change the and to an or in the negation, A does not divide B minus C, then A does not divide B, or A does not divide C, right? And of course, the contrapositive is true, which is true since it is logically equivalent to P. Great. So we have one final question left on the midterm, and that is, a question about strong induction. See, we're even nice. We even tell you that it's strong induction. We don't even tell you what kind of induction. And we've got a whole, 35 minutes to spare? We're going to crush it on this midterm, gang. We are going to crush it on this midterm. Okay. So, the sequence, we have a sequence A naught, A 1 dot 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 dot, defined by A naught equal to 1, A 1 equal to 2, A 2 equal to 3, and for all n bigger than or equal to 3, we have an is equal to an minus 2 plus 2 times an minus 3. Plus 2 times an minus 3. Okay. And we want to prove by strong induction, prove that an is strictly bigger than 3 over 2 to the power of n for all, let's say, for all n in the integers where n is bigger than or equal to 1. Okay. So what do we need to do? We need to first set up our base case. So base case. What am I going to do? Base case. So definitely, I'm going to want to prove it for the first few values by hand. I don't know how many I'll need, right? Because I know I'm doing strong induction. So I'm not exactly sure how many base cases I will need. I suspect that since my sequence has sort of 3 seed values, right? So there's 3 values I have to define by hand before I define this recursive sequence. I'm going to suspect that I need to do at least 3 base cases, right? So let's do that, and then maybe, let's be open to the fact that we may have to do more base cases depending on how the situation shakes out. So base case, for n equals 0, so let's actually think for a moment. Let's go over to our rough work and think about how we're going to do this. So, what I'm thinking is that we have a naught. We have a naught. We want to prove that that is bigger than 3 over 2. Hang on a second. Oh, for all integers bigger than or equal to 1. So our base case should not include n equals 0. So we have a1. We want to show that that's bigger than 3 over 2 to the 1. So that's that 2 is 3 over 2. Now, again, we don't want to rely on, we haven't talked about decimal expansions at all in this course. So we don't want to rely on things like decimal expansions. We do want to rely on the fact, though, that we can divide both sides. And so we could start with an inequality. So notice this is all to the right of this dark blue line, or dark teal, whatever Windows called it. So we start with this obvious fact, and we move back to here. So for n equals 1, what are we going to do? Well, we could write something like 4 implies 4 is greater than 3. So start with an obvious fact. This implies that 2 is greater than 3 over 2, which implies that a1 is greater than 3 over 2 to the 1, right? For n equals 2, now I want to do a similar thing here. So what is that? So a2 has to be bigger than 3 over 2. Well, I don't want to get my colors confused with the good copy of my proof. So a2 has to be bigger than 3 over 2 to the 2. So so that's 3 over 9 over 4. And so that would be equivalent to 12 over 9. So I want to start with this obvious fact and work my way back, right? So for n equals 2, we have 12 over 9 implies 3 is bigger than 9 over 4, and 9 over 4 is equal to 3 over 2 to the 2, and this implies that A2 is bigger than 3 over 2 to the 2, right? And I suspect, okay, let's leave it here. Let's leave it here and see what kind of base cases we actually need, right? So let's go over, let's do some rough work. Let's leave ourselves some space. Leave ourselves some space for some more base cases, potentially. And now we would say something like inductive step. So we'd say something like, suppose that for some k in the integers, where k is at least 1, suppose that for all I between 1 and k, a sub I is strictly larger than 3 over 2 to the power of I. All right, so that's what it means to assume strong induction, right? That's what we're assuming. Now, what do we want to prove? We want to prove the statement for AK plus 1. So let's think about this. So AK plus 1, how could I say something about that? Well, I need some way to relate it to lower terms. And I know that I have this recursive sequence, right? I have this recursive sequence here. So AK plus 1, I can re-expand as K, let's go one sub at a time. K plus 1 minus 2 plus 2 times A K plus 1 minus 3, right? Is that, did I get it right there? Yeah. So, but notice this formula only holds if K plus 1 is greater than or equal to 3, which is exactly the case when K is greater than or equal to 2. So we understand now that actually in our inductive step, we will want to assume that K is greater than or equal to 2. We may want to assume something even stronger. And so definitely it's a good thing that our base case did go up at least to K being equal to 2. Okay. So now let's simplify this expression a little bit. So what would this be? So this is A, K plus 1 minus 2 is A K minus 1 plus 2 times A K minus 2. Yeah. And right, so let's just also check here. We want K minus 2. We want to make sure that that is not 0, right? Because it can't be true for 0, and we're going to want to use the induction hypothesis on both of these things. So we want to make sure that K minus 2 is at least 1, which means actually we want K to be bigger than or equal to 3 in order to apply our induction hypothesis, right? So actually we realize, oh no, I'm going to need one more base case. It's a good thing I left myself some room here. So for n equals 3, and again, we're just gonna work this thing backwards, right? So we want A3 to be bigger than 3 over 2 to the 3, which is A3 we're going to need to work out using the recursion formula. So what do we have here? So A3 is equal to A3 minus 2 plus 2 times A3 minus 3. So this is a of 1 plus 2 times a 0. A of 1 is 2. A of 1 is 2. So this is equal to 2 plus 2 times 1. Ooh, I did not leave myself a lot of space. This is going to make for a messy midterm, which is equal to 4. Okay. So we need what? We need A4 to be bigger than, or sorry, A3. I already wrote it here. So this should be 4. This is going to be 3. So 9 times 3, 27 over 8. 8 times 4, 32. Bigger than 27. So again, we could do something like, yeah, if this was the midterm, I would erase and move this down. Thankfully, I have this cut and paste tool, so I'm just going to cut and drop it down a little bit. I mean, that's all the more reason why, I probably should have done the rough work for induction before I was a little overzealous writing induction stuff here. I probably should have done the work before I wrote that. Then I would have seen from the rough work I needed one more case. So, where are we here? Right. So then we get hence 32 bigger than 27 implies 4 is bigger than 27 over 8 implies 4 is bigger than 3 over 2 to the 3 implies that a sub 3 is bigger than 3 over 2 to the 3. Okay, fantastic. Now, let's go back over to our rough work, right? So we've just, all we've done is just repaired our base cases. Let's go over to our rough work. So what the corresponding statement here would be by the induction hypothesis is that this is bigger than 3 over 2 to the k minus 1 plus 2 times 3 over 2 to the k minus 2. Okay. And what are we trying to show? Ultimately, we're trying to show, again, it's a very good thing I'm doing this over here in rough work, right? I wouldn't want the grader to think that I'm assuming the thing I'm trying to prove. We're trying to show that this is bigger than 3 over 2 to the k plus 1. So it would be enough if I could just argue that this stuff was bigger than 3 over 2 to the k plus 1. That would be enough, right? So how can I try and put all of this in common terms and argue that? So one thing to try and get it closer is maybe I try and put this all into one fraction, right? So this is k to the 3 minus k over 2 to the k minus 1. I don't want to cancel out this 2 here because I actually want to add a factor of 2 down here, right? So I actually want to multiply by another 2. So this would be 2 times 2 times 3 to the k minus 2 over 2 times 2 to the k minus 2, right? So what do I get? So this is 3k minus 1 plus, 4 times 3 to the k minus 2 over 2 to the 2 to the k minus 1. Okay, great. We've made some progress. Now probably I see that 4 and I'm already suspicious. I'm like, well, 4 is equal to 3 plus 1. So I'm suspicious. Maybe it will help me. Maybe it will help me to write that as 3 plus 1. Might get some more, multiples of 3 in here. But let's hang on for a second. What am I trying to prove? I would like to show that this is bigger than 3 over 2 to the k plus 1, right? So if I can just argue that this thing if I can argue that this thing is bigger than, well, I can get rid of the what am I saying here? Okay, I can try and multiply this denominator across, right? So I'm going to get 3k minus 1 plus 4 times 3 to the k minus 2 bigger than 3 to the k plus 1. And what do I have in the denominator here? I'm going to have 2 squared. I'm gonna have 2 squared left over. Okay. So what else could I do? Well, I could factor out some 3's. I could factor out some 3's here. So I could take out 3 to the k minus 2. Now I should probably check that that's still an integer, right? So I would need 3 to the k minus 2 to at least be 0. So I would want k to be at least 2. Okay, good. That's within our base cases. So I factor that out. I'll be left with 1, 3 in the middle here, plus 4 bigger than 3k plus 2 over 4. I can divide both sides by 3k over 2, multiply both sides by 4. So I get 4 times 7 on the left side. And this should be bigger than, what am I going to be left with? 3 squared on top. So 4 times 7 is 28, is bigger than 9. Great. And that's an obvious thing. So now I just have to run this whole proof. I basically just have to run this whole proof backwards, right? Well, we could there's a few different ways we could do this. So I ultimately want to prove that this term, this is the thing that I ultimately want to prove. So let's show this first, right? Let's show this first. So let's work backwards through these steps. So we have what? So we have 28 is bigger than 9, implies 4 times 7 is bigger than 3 squared. Implies, sorry for all the jumping around. So implies, let's say 4 times 3 plus 4. 3 plus 4 is bigger than 3 to the k plus 1 over 3 to the k minus 1, was it? Is that correct? No, hang on a second. What have I done wrong here? No, hang on a second. This is 3. Okay, I'm not going to edit this out. I'll leave this in because this is realistically how these things go, isn't it? This is realistically how these things go. 4 times 3 plus 4. Because this is a minus 2, and so that's a 3, and then that's going to be a 3 squared. It's okay because it's 27. Right, sorry, this should have been a 3 to the power of 3. Which is okay because this is a 27. Right, okay. Okay, we were able to save it quick there. So 28 is bigger than 27, which is bigger than, what do I have here? This is 3 to the 3. Here we go, yes. And this implies that 3k minus 2 times, what was it, 3 plus 4 is bigger than 3k plus 1 over 2 squared, which implies, so we're just going backwards through all the steps that we had just worked through, which implies that, let's see, so we could go 3k minus 1, so we go 3k minus 1 plus 4 times 3k minus 2 over 2 to the, what do I want to divide by? 2 to the k plus 1? 2 to the k plus 1 or minus 1? 2 to the k minus 1. Bigger than 3 times k plus 1 over 2 to the 2 times 2 to the k minus 1. And this implies 3k plus 1. Where did that all come from? Oh yeah, I want to separate out the other side, right? So this becomes 3 over 2 to the k minus 1 plus 3 over 2 to the k minus 2 bigger than 3 over 2 to the k plus 1. And so let's label this, because this is we're going to want to use this equation here. So I'm gonna give this a label. I'm gonna put a 1 with a circle around it. So now I want to go ahead and do the induction proof, right? So I've set up my inductive step, but now I want to say something about ak plus 1. And it's important for us that that k is bigger than or equal to 3, right? So we could say something like, since k is bigger than or equal to 3, k plus 1 is bigger than or equal to 4, and that allows us to use the recurrence relation. So ak plus 1 is equal to let's say k plus 1 minus 2, I'm just going step by step, plus 2 times ak plus 1 minus 3, which is equal to k minus 1 plus 2 times k minus 2. And now we want to use the induction hypothesis on k minus 1 and k minus 2, right? And so the induction hypothesis says that we're allowed to use this fact for all I between 1 and k. So we just need to verify that that k minus 1 and k minus 2 are in fact between there, right? And that was the whole point of us taking k to be at least 3, right? So we could say something like, since since k minus 1, k minus 2 are both less than k, and we need to argue that they're both bigger than 1, and so we could say, and k is assumed to be at least 3, which implies that k minus 2 is bigger than 1. Now we get that k minus 2 is at least 1, k minus 1 is at least that, so those are both in k. Hence, we may apply the induction hypothesis and we get that. So I would just, to be extra clear to the reader, I would repeat the last inequality that we obtained. Then I would say this is strictly larger than 3 over 2 to the k minus 1 plus 2 times 3 to the 2 k minus 2. And we could even say, we could really drive the point home that that's by the induction hypothesis. And now I also realized I made a typo up above. This should have been a 2. And that is, I get in trouble. That's because I jumped ahead. I should have put one more step of calculation in between these. So let that be a lesson to everyone. There's more than one reason why you want to show every step of calculation, not just to make it absolutely clear to the person grading your assignment as to what you're doing because you want all the marks, but also to make it perfectly clear that to yourself what's happening, so you make sure you don't miss any of those things, right? And so finally, we know that this is bigger than 3 over 2 to the k plus 1, and now we could reference, by equation 1. And that's it, right? So therefore, we have shown by induction, by strong induction, if you like, that a(n) is strictly bigger than 3 over 2n for all n. For all n bigger than or equal to 1. Okay. And that's it. If you have comments, questions, concerns, drive up engagement on my channel, drop them down below. Yeah. Otherwise, I'll see y'all very soon, and I'll leave you off with a QED.